All right, so before we go on to more proof, so somebody asked to talk about the programming assignment, so I posted this up about a week ago, I think. But programming assignment 1 is due on the 25th. And it's a program to let you play around with sets and set operations. So let's look at the description of it. So I'd like you to write this in C, and I'd like you to do it on the Linux server. And you're writing a program that basically lets you input the elements of two sets and then performs different operations on them, shows you the elements of a set inside curly brackets with commas in between. The cardinality, that's just the size of each set, how many elements are in each set, what's in the union, the intersection, and what's in A take away B. So you run your program, it should ask the user to input a string of characters that it uses to build the first set, and then ask for a string of characters to build the second set. If the user types an element more than once, it just goes into the set once. Okay, if they happen to type the character 5 times, it's only in the set once. So you have to do some cleaning up of the input. You can ignore spaces, but anything else can be an element of the set. It can be uppercase letters, lowercase letters, numbers, punctuation, anything except spaces, tabs, new lines, right? So-called white space. The empty set is valid, so if they just hit enter, that's an empty set. Okay. And you can just upload your .c file through Canvas. If you have multiple files, put it into a tarball. If you're splitting it into files, you probably know what a tarball is. Make a tar or a TGZ and upload that. But if it's just a C program, just upload the file .c through Canvas. And let me show you what this does, and then talk about how to do this. So you can assume that there's no more than 120 characters on each input line, and that the user is only going to type in normal characters. They're not going to put in like a control 7 or something like that, so printable characters. And so I just added a note in here saying C/temp/PA1215 for a sample solution. So if you're on the server, you can run /temp/PA1215 and see an example of what this should do. So enter set A, let's say this has ABC, and let's say this has DEF. Okay, so show the elements of A, elements of B, the cardinality of each set, the union, the intersection, and A take away B.
Now, is that is space function, will that capture anything that's considered a white space?
Mm-hmm.
Okay.
Yeah, that's exactly what it does. So if I do hello and hi, hi, how, the elements of set A are HELO, the elements of set B are HIOW. Cardinality of each is 4, and there's the union, intersection, and takeaway. Ignore that. That's not what should happen. Okay, so my code doesn't work with spaces correctly. I'll fix that. If A is hello and B is the empty set, right? Set A has HELO, set B is just bracket bracket. Cardinality of A is 4, B is 0, union, intersection, takeaway. If A is empty and B is not empty, right, you get similar but different results. And it should also handle the case where A and B are both empty sets, and then basically everything's empty, cardinality is 0. Okay, so there is an easier way to do this, and there is a really hard way to do this. So this is one of those important moments. where you might save yourself a lot of time if what I'm about to say makes sense. So here's my recommendations, besides starting early. Okay, don't try to do this an hour before it's due. If you like structures, you can use structures, it's not necessary. First thing, you need to think about how are you going to store these sets in your program. And since a set is just a collection of characters, and it can't include weird characters like null terminators, you can store a set as a simple string in C, just an array of characters. And that gives you all kinds of things like string length and string compare and all these other functions built into the string library for manipulating strings. You can print them out with a printf with %s and so on and so forth. So my recommendation is store your arrays, store your elements of a set as just a simple string, just an array of characters. There's other ways you can do it, but that's probably the most straightforward way. Once you've figured out how you're going to store it, write a membership test function. Okay, so what does this look like? Something like integer is member. And your first argument might be a string called set, and your second argument might be a character called element. So I've got a set. I'm assuming it's a string of characters. I've got a set, and I have a particular element, which is just one character, and I want to know, does this element belong to this set? That's what this function does. And it returns, say, a 1 if it's in the set and a 0 if it's not. So return 1 if the element is in the set, otherwise 0. And how do you do this? Make a for loop. Go through every character of the set, see if it's equal to the element. As soon as you find a character in the set that equals the element, just return 1. You're done. You found it in the set, don't have to do anything else. But if you go all the way through that for loop, you check every single character in the set, and none of them are equal to the element you're looking for, then you return 0. And you can safely say the element is not in the set. So that's not a bad function to write. It's a for loop with a couple of ifs. Okay, if you have a membership test function, it's very easy to build a set that gets rid of duplicates. And so how do you do this? Start off with a set that's just equal to the empty set, which is just a string of length 0. Read a character from the user. And if that character is not already in the set, add it to the set. And just keep looping until you reach the end of the input. So how do you read a character? Well, you use fgets or something to read a string of characters from the user, and now you do another for loop to go through each character that they input. And for each character, you say, is it a member of this set? Well, how do you know if it's a member of the set? User is member function, right? And if it returns 1 saying it's in the set, don't do anything. But if it returns a 0, then you want to add your character to the set. Well, how do you do that? Append it to the end. So you can do that using string cat function, or you can just use it by adding it to the end of the array. It's one statement either way, but you got to think about exactly how you're going to do that logic. So read a character. If it's not in the set, add it to the set. That's how you condition your input. So if the user types in HELLO, well, you'll add the H, you'll add the E, you'll add the L, but when you see the second L, you'll say, is it a member of this set? Yes, it is. I'm not going to add it. You get to the O, you're going to add that. And so your set will end up looking like a nice, clean set with things only appearing once. Now you've got conditioned sets. So how do you do the union? So you got two sets, A and B. Well, make an empty set. Go through each element of A and just add that element to the set S. You're basically just copying A into your output set here. So go through each element of A and add that element to your output set. And then, for I equals 0 to last element of B, if element I is not already a member of set, then add element I to the set. So again, use your membership function. First copy set A to your output set, then go through each member of B, and if it's already a member of your output set, don't add it. If it's not, go ahead and add it in. How do you do the intersection? So this is union. How do you do intersect? Start with an empty set. For I equals 0, the last element of A, if element I is a member of set B, then add it to your output set. If it's a member of B, then add it to your output set. So just pick one of your sets, say A, go through each element of it, and if that element is also a member of B, add it to your output because it's in the union. You could start with B instead if you want. It's going to get you the same result. And then A take away B is the same thing. For each element of A, if the element is a member of B, then don't add it to the output set. Otherwise, do. So if you think of these things, these operations, union, intersection, and so on, as saying, let's start with an empty set and let's add things to that to get our desired output, then it's usually one loop with something testing membership inside. But all of this hinges on coming up with a way to define sets, coming up with a membership function. And it's not really difficult to do either of those. It's just something you want to nail down first. And then these other things kind of fall into place. And if you're storing your sets as strings, to find the number of elements, just use a string length function. And that'll tell you how many characters. That's the number of elements since you have no duplicates. And you can exercise this code because it's pretty easy to make a set if you're using strings. Just, A equals double quote, blah, blah, blah. You can do that in your C program, and you can start off with, only defining sets that don't have duplicates, and just work on your union or your intersection, for example. So there's a lot of ways to kind of build this up from simpler to more complex to the final version. So does that make sense? So I'll fix the sample code so it ignores spaces, but other than that, the code that's in /temp PA1215 should be a good guide for what you're after. Alright, so let's go back to proofs. So I'll leave our definitions of even odd up there. And we've just proven two things. We know that if n is even, then n squared is even, and if n is odd, then n squared is odd. So let's prove something new. Let's prove that if n squared is even, then n is even. And this does not automatically follow from what we've done so far. This is the converse of our first thing that we know. And converses aren't logically equivalent. But we can prove this pretty easily using what we know so far. And if you do an indirect proof, it's almost trivial. So let me show you an indirect proof. So n squared is even, that's a hypothesis. We want to prove now that n must be even. Let's suppose that n is not even. That's an assumption. Well, if n is not even, it's got to be odd. We haven't actually proven that, but we could prove that pretty easily from here. So n is odd. Well, if n is odd, what do we know about n squared? Yeah, n squared is odd. And we know that because of this. So we've just proven that if n squared is even, n squared is odd. That's a contradiction. Therefore, n must be even. Right, this assumption led us to a contradiction. So n must be even. And that's all we need to say. And we can do exactly the same thing to show that if n squared is odd, then n is odd. Right, how do we do that? N squared is odd. Suppose n is even. Well, if n is even, n squared is even, but we just said n squared is odd. There's a contradiction. So if n squared is odd, n has to be odd. That doesn't always work that easily. It happens to be that the converse of this statement is true. That's not always going to be the case. So for example, if n equals 6, then n is even. Well, we can prove that. Right? We can just say 6 equals 2 times 3, and 3 is an integer. The converse of this is if n is even, then n equals 6. Well, there's no way we can prove that this is a true statement because it's not a true statement. N could be 10. N would be even, but it would not be equal to 6. So this is not even a logically correct statement. It's certainly not logically equivalent to this original statement. Right? So that's false. But for this n is odd, n squared is odd kind of thing, converse actually works. But you got to make sure it works because it's logical. All right, let's end with a fun one. Let's prove the square root of 2 is irrational, meaning it can't be written as a quotient of integers. Okay. There's no pair of integers a and b such that a over b equals the square root of 2. So let's do a proof by contradiction. So suppose square root of 2 equals a over b, where a is an integer and b is an integer. And I'm going to throw one more condition on a and b, which is a and b are not both even. One of them can be even, but not both. And that's not really a restriction, because if they're both even, we can divide them both by 2, and we'll still have 2 integers. And if both of those happen to be even, we could divide them both by 2, and since they're even, we'd still have 2 integers, and their quotient would still be square root of 2. So in other words, I'm just saying, let's put a over b in simplest terms, right? Get rid of any common factor. And so they can't both be divisible by 2. Okay, so here's how it goes. Square root of 2 is equal to a over b. So 2 is equal to a squared over b squared. I'm just going to square both sides. And so 2 times b squared is going to be equal to a squared, which means a squared is even, which means a is even. And we just showed if the square of an integer is even, then the integer is even. Okay, now I'm going to go back over to a new column. Well, since a is even, we can say a equals 2 times some integer, which means a squared equals 4 times some integer squared. And we can take this and rewrite it as 2b squared equals, instead of a squared, I'm going to write 4 times I squared. And divide by 2, b squared equals 2 times I squared. Well, I squared is an integer, b squared is twice an integer, so b squared is even. And by what we showed a few minutes ago, that means b is even. And so if the square root of 2 can be written as a over b, a and b are both divisible by 2. Which means we can divide them by 2 and get smaller numbers a and b whose quotient is the square root of 2. And we go through this, and those are going to both be divisible by 2, and we can do this forever. In other words, we violated this original condition that a and b are not both even. And by starting with the square root of 2 as a over b, we showed that a and b are both even. It's a contradiction. And that's all we need to conclude. Square root 2 is not equal to a over b for any ab in the integers. And so the square root of 2 is irrational. So that was a proof the Greeks came up with thousands of years ago. To me, it's not a very warm and fuzzy proof. There was nowhere along the way where I sort of like had a clear sight where this proof was going when I first saw it. It just kind of at the end you have to nod your head and say, yeah, I guess you're right. But it didn't really convey a lot of insight as to where this proof is coming from or why this works. But it doesn't have to be a valid proof. It has to for you to discover it. But when somebody has discovered it and presented it, you can look at it and you have to reach the same conclusion. There's no fraction that's equal to square root of 2, which is a pretty powerful conclusion. So that's a good proof to have seen at least once. And like I said before, that's the one that kind of wrecked the whole idea of whole numbers being the key to everything, because it can't even get to the length of a 1-1 triangle's diagonal. So, but that's a cool result. All right, so questions. So I posted some homework questions, and they will look an awful lot like what we've been doing in class today. Okay, but I want you to write up the proofs of these in a way that you understand what you're doing, and that creates a logical proof. So they're basically, most of them are the questions we've already done, the proofs we've already done. But I want you to not just copy from your notes or the video, right? Actually think about the steps. But having already seen the proofs, right, it will be a little easier than just kind of a random proof. But think about what you're doing as you do it and ask questions. Okay, so the homework's due Friday. This week's homework was Monday because we didn't have class last Friday. The homework that I just posted. Today is due on Friday, so work on it before Wednesday's class and then bring questions to Wednesdays, and we'll talk about it then. All right, so I will see you next time.